Thank you very much. It's very nice to be here in Minsk. It's always a pleasure to participate here in our conference. I'm sorry I started to write the title of my talk in Russian, but I'm glad that we have foreign participants among our audience here, and so I will speak in English. Let me start from a very general words, because I'm going to discuss today algebraic transformation group. So we have X. This is some irreducible algebraic variety. I consider this over field K. And I'm sorry, this field is supposed to be algebraically closed. And of characteristics zero. Sometimes people ask, why do they have such restrictions? Again, we have polite and unpolite answer. The polite variant is to find some reasons, something like we need exponents, and in exponents theory we have some denominators. That is why we ask for characteristic zero. But unpolite answer, this is mainly not polite, but this is a lack of education. Some people know everything, some people know only characteristic zero. So in my case, to be on the safe side, I would prefer to consider only characteristic zero. Okay, and we are going to study algebraic transformation. What does it mean? We have some algebraic group G. Mostly we consider linear algebraic group or the synonym affine algebraic group, but theoretically we may consider any algebraic group, and it acts by regular automorphism on our variety. By action we mean a map, which is an action in the set-theoretic sense, and this map should be amorphous.
Is it a full automorphous group?
No, this is some automorphous group. Variety, you'd say, maybe a fine and make a future automorphous group, but we consider only finite-dimensional algebraic subgroups. And we ask about natural properties, about questions, orbits, invariants, geometry, and so on. But usually people study a particular case. No, maybe other way around. If you consider arbitrary actions, then these actions are constructed from some blocks, from some pieces, and these pieces are orbit closed. So, important particular case. This is the case when we have an action with an open orbit. So we have an open subset in our variety X, open in the Zariski topology, such that our G acts conjunctively with this open subset. So this open subset is some homogeneous space, G over H, where H is a closed subgroup, algebraic subgroup inside of G. Such a variety always have a structure of quasi-projective algebraic variety, and this is an open subset inside of X. And in this case, we may say fix our open orbit, fix homogeneous space.
G is without.
Not now. For a moment, this is arbitrary algebraic. And in this case, we may study all possible embeddings. So this is equivalent embeddings of a given homogeneous space, G with H. And even more particular case, this is the case when we have a group embedding, when we embed our group G inside of X, but I would like to consider G as a group variety with respect to both left and right multiplication. So as a homogeneous space, my G will be G times G over the diagonal. Delta G. Okay, and I would like to study all varieties which contains G as the open subset and the action of G by multiplication on the right and the action by multiplication on the left. They can be continued to the whole variety X from this open subset to the boundaries. And in this case, I say that we study group embeddings. And now I would like to make a psychological observation that people study mostly the case when G is reductive. This is a very important case, and there are several reasons why people study the case of reductive. First of all, again, correct answer. Because this is very natural, reductive groups, they include algebraic tori, they include special linear group, general linear group, and these actions really here in practice and you need this concept. But there is more specific answer that in this case we have some technique which works. We know how to deal with a reductive group. By definition, if we work over algebraically closed field of characteristic zero, reductivity means that we have Maschke theorem. Any finite dimensional regular representation is a direct sum of simple submodels, direct sum of reducible subrepresentations. We have some structure theory of these groups, we have roots, we have maximal tori, so we know what to do. But we may ask, why should we restrict only to the reductive case? Can it be generalized to arbitrary group, or if you are interested only in linear algebraic group? Any linear algebraic group is a semi-direct product of reductive part and unipotent product. So there are two extremes, either reductive or unipotent. And if we want to move from the reductive case to the more general case, the first object to study are actions of unipotent groups. At the first glance, unipotent groups are a very simple object. Any unipotent group, by more or less by definition, or it follows from definition, there is a closed subgroup in the group of upper triangular matrices, with units from the diagonal. But the structure theory of such group is quite mysterious. When you go, say, by dimension, in small dimension, you can find all such groups. But when you go, say, about dimension 10, this is just some lists, some families, and there is no such a tool to study them. But let us concentrate on a simple case. So our situation for today's talk is the case when G is unipotent commutative. And what does it mean for a group to be unipotent commutative? Again, easy exercise. I always recall that we have this assumption. It means that our group G is just the vector group. So we take GA, where GA is an additive group of my ground field. And we take just the direct product of this GA as itself several times. So this is just an additive group of the vector. No other commutative unipotent group, only one group in each dimension. And again, this is automatically connected. Any unipotent group of zero is connected. Okay, so I'm going to study group embedding for such G. But in this case, I may assume, without loss of generality, that my homogeneous space, my open orbit, is G itself. Because for commutative group, if I have such an H, which is a stabilizer in an open orbit, stabilizer of the general position, then they are all conjugate among the point of open orbit. But if my group is commutative, so H acts trivially on the open orbit. And as it is an open statistic subset, then H acts trivially on the whole X. And so if I assume that my action is effective, then without loss of generality, this is the equivalent of effective. My open orbit is identified with the group G. Okay? We might consider the case when X is affine. But here, situation is trivial because for unipotent group action, it is known that all orbits on affine varieties are automatically closed. So in this case, we have only one group embedding Namely, X is the group G itself, nothing else. So, if you compare this case with the case of toric varieties, these are varieties with an open subset, which is a torus, and this is glued from invariant open charts. In this case, we don't have possibility to construct such gluing because there are no invariant affine charts. The only affine variety is an open chart that is group itself. But nevertheless, we would like to consider the complete case. And here we have some, at least something interesting. So our group G, inverts in X, and this seems to be interesting. And this will be the subject of my today's talk. I would like to fix the corresponding definition because I may consider this like a group embedding, but in more convenient terms, I would like to say that an additive action this is an action of my commutative uniform group on some variety X. This is an open group, so I assume that action is effective, and with an open group. Equivalently, this may be considered as equivariant completion of an affine space. Because my group is isomorphic at the algebraic variety to the affine space, any unipotent algebraic group is isomorphic to an affine space. But if the group is commutative, then it even has the natural structure with respect to this affine space, just pairwise addition, pointwise addition. And I consider open embeddings of such affine spaces. But equivariant means that this my group structure on this open subset extends to an action on the complement via such a regular number. Okay, and so there is some theory concerning such equivariant completions, and we tried with Yulia Zaitseva, who is the author of my work, we tried to collect all known up to now facts about such actions in our survey. We put it on archive. The last version is on this month, and we hope very much that it will be released the last version. We will not update. It looks to be in a final form. It will be published in Russian Mathematical Surveys. And this is a really a survey text. So we collected many facts which are known about this type of actions. It turns out that there are many facts because there are several techniques which allow to study such actions. But in this talk, I would like to concentrate on one technique called Arzhantsev correspondence, and also to present some original results which were not known before and which we included in this survey text. So now this was introductory part 1, and now I go to part 2. I would like to explain what is the Arzhantsev method of Arzhantsev correspondence. This subsection will be called finite dimensional algebras. Because this correspondence is really about Artinian algebras or equivalent to finite dimension. I would like to generalize my problem a little bit, consider not only commutative unipotent, but any commutative linear algebraic. So recall, if G is commutative linear algebraic group, and if it is connected, then G is nothing but, again, direct product of additive groups, GA that we put here as, and I can also take torus, GMR. So the only commutative linear algebra groups, if they are connected, they are product of one-dimensional subgroups, additive and multiplicative. And I would like to consider group embeddings for such case. But there are many of them. It's not easy to describe all of them. I can fix not only the group. This is not one group, this is some platform, because this S and R, they can vary. But I would like to also fix some variety. And the first candidate to consider is the affine space. Sorry, this is a projective space. And about the situation, there is a nice theorem by Knopf and Lange. It is proved in 1984. And in this theorem, there is some correspondence is established. So the left part in this correspondence is the case of, group embedding. So my group is commutative linear algebraic. Action is effective, and it has open orbit. And it turns out that such group embeddings are in one-to-one correspondence with commutative associative algebras with unity. So A is commutative associative algebras with unity. But this is not something like polynomial algebra. This algebra is defined in dimension. And the dimension of this algebra is n plus 1, where n is the dimension of this projective space and the dimension of my group, because my group is an open subset. So we have a one-to-one correspondence between such algebras and such group embeddings. In one direction, this is quite easy. If I have such an algebra, okay, then I may take G to be the group of invertible elements of my algebra. Modulo scalars, non-zero scalars. This will be commutative linear algebraic group, and it acts on the projective space, which is just a projectivization of my algebra A. And so my correspondence in this direction, if I want to explain that this construction really gives me group embedding, I should note that firstly, the subgroup of invertible elements in my finite dimensional algebra is open. I have one invertible element, namely unity. I assume that my algebra has a unity. And it's clear that to be invertible means that some determinant is non-zero. So if something is non-zero, then we have an open subset when it is non-zero. So the condition to be invertible is such algebra is open. So this is an open subset of an affine space, and this is really an affine algebraic subgroup. But there are no quasi-affine algebraic subgroups. This is automatic. And also, we have a natural action of this group just by multiplication on my algebra, and so on the projectivization of this algebra. But as it is a projectivization, then scalars act serially, and I have effective action of the vector group. I should take quotient by my scalar elements, which are just proportional to the unit element. And open orbit in this case is just a projectivization of this open subset. And this is indeed open in the projective case. Okay. Another direction. It seems to be not so trivial, because when I have an algebra, this is more or less clear how to construct a group. But when we have a group action with an open orbit, it's not clear who will be our algebra A. But Knoop they propose very elegant and short arguments. Namely, I have my G, which acts effectively on Pn. So it means that this is a subgroup inside of the automorphism group of the projective space. So this is P, G, N plus 1. So this is a subgroup here. And I would like to consider natural projection from general linear. Just taken open by itself. Let me denote this projection by phi. And then I consider the preimage of the I denote it by H. Now this is some subgroup of the matrix. The dimension of this H is n plus 1, because G acts here with the open orbit, so it is n-dimensional, and my kernel of this projection is the group of scalar matrices, so fibers are one-dimensional, so the group H has dimension n plus 1. It is not clear immediately why this preimage is commutative. G is commutative by my assumption, but the preimage may not, but it is commutative because let me take the derived subgroup of this H. Since this G is obtained as a quotient of this H by one-dimensional torus, and the factor group is commutative, it means that the derived subgroup is contained in this subgroup of scalar matrices. But this is some linear group. And if you consider the derived subgroup of a linear group, the element of derived subgroup will have determinant 1. So you have that any element have determinant 1. So it implies that derived subgroup is trivial. And so H is commutative. But up to now, there is no algebra A, so we should find some algebra. And now this is quite easy. We just take A to be just a subalgebra inside of the algebra of matrices generated by this subgroup H.
Just a linear span of
just a linear span of H. H is commutative, so A is commutative. But the question is, maybe it has higher dimension. My subgroup H is n plus 1 dimensional, and I consider linear span. This is some, I don't know, currently embedded subgroup, and maybe the linear span is higher dimension. But it cannot be higher dimensional just because I may take now the group of invertible elements in this A and act on the n plus 1 dimensional vector space, which I identify with my A. Which is, no, it's not my A, which I identify with the vector space on which the matrix algebra is an algebra of linear operators. And this action is effective just because this is a subset in the matrix algebra, and it has an open orbit. Just because H acted on this subset with an open orbit. It acts on a projective space with an open orbit. And now I take into account this one-dimensional kernel, one-dimensional torus, so I obtain open orbit on my vector space. And in this case, we know that the dimension of the group of invertible elements is n plus 1, the dimension of my space. So H is a subset in this subgroup of invertible elements. So we conclude that H is nothing but this across, and dimension of my commutative algebra A is again inverse. So quite elementary reasons show that this way we obtain finite dimensional algebra, and the action of G on Pn, this is exactly the action of the group of invertible elements on the projectivization of my. So this was point number one. Knopflander observed that such invariants are in correspondence with finite dimensional commutative associative algebra. I would like to take story number two. But before coming to the story, I recall basic fact on such finite dimensional algebras. So let me recall some facts. They're quite elementary, not so well written in the basic textbook, that any such algebra commutative associated with unit is a direct sum of local algebras. Okay, and I will put here strange index R plus 1, because in Knopflander correspondence, it will correspond to the group of rank R. So the number of semata will denote by R plus 2. And here, each AI is local. So if we want, say, to classify this algebra to study the structural theory, we should concentrate on the building blocks on local algebras. And for each local algebra, AI, one can prove that this is isomorphic to the ground field plus maximal ideal. So by definition, there is a unique maximal ideal, and these are constants, these are elements proportional to the unit. And this maximal ideal is always nilpotent. So the set of invertible elements in my algebra is just a complement to this hyperplane, to this maximal ideal. Okay. And do we know classification of such finite dimensional algebras, say of local ones? Yes, there is such a classification. I will tell something about this, but only in small dimension. In general, this is not known. But before coming to this classificational result, I would like to recall the theorem of Arzhantsev. This is 99. And it against some correspondence between some algebraic object and representations, in this case, something like this. So I would like to consider faithful cyclic representations. This time I will consider not any commutative linear algebraic group, but only unipotent commutative algebraic group. So GAN. And representation is in the general linear group of some other parameter M and M are independent. But I consider only cyclic representation. It means that there is a vector whose orbit span is a whole vector space. So it turns out that such representations are in one-to-one correspondence with the following pairs: A and U, where A is again commutative associative algebra with unit. But this time I think this is local, and its dimension equals the dimension of the space where we have our representation with this number M. And this U This is a subspace, not only in my A, but more precisely in this unit maximal ideal, in this unit maximal ideal M inside of A. And we have two conditions on this subspace. Firstly, this subspace should generate our algebra A. And secondly, the dimension of this subspace equals M, this M. So we have M and M. Okay. Maybe I will not explain how this correspondence works, but at least if we restrict this theorem to the case when M is n plus 1, then when we have a group inverting into projective space, so the corresponding vector space has dimension n plus 1, then in this case we don't need the subspace because the subspace will coincide with the maximal ideal. The subspace should be hyperplane in my algebra. This is some algebra A, and I have a subspace in my algebra. And I can generate a subalgebra by this subspace inside of A. So this should be the whole algebra. Subalgebra this unit. Yeah, because this is the subspace is the maximal ideal, so it should generate this. Okay, so when we restrict, I will put it as a corollary. When we restrict it to the case of GAN adjacency on PN, effective and with an open orbit, then both from the Toplandy theorem and from the Spatuchinkel theorem, we will obtain one-to-one correspondence with local algebras without any additional subspaces, any additional data, whose dimension is n plus 1. And the effect is that there are many local algebras. And it shows that there are many group embeddings for projective spaces. And this is quite strange. So we have many different actions of such a commutative uniform group with an open orbit on the same orbit.
So you consider actions up to what?
Up to natural equivalence. Two actions are equivalent if there is an automorphism of my acting group and automorphism of my variety, which sends one action to another.
Yes, and algebras up to isomorphism, right?
And algebras up to isomorphism. So everything is as natural as possible. Okay, but how many algebras do we have? There is an information about this. Namely, if I put here the dimension of my A, where A is local, and here I have the number of isomorphic classes, then there is a following table. If my algebra is one-dimensional, then technically this is nothing else but the ground code. No chance. If my algebra is two-dimensional, then again only one local algebra, namely polynomial algebra C of x over x squared is one important one. So only one isomorphic class of local two-dimensional algebras. If you have dimension 3, then the situation is a little bit interesting. We have two algebras. First thing, k of x over x cubed and k of xy or x squared, xy, and y squared. Okay, so we have two algebras. After items, one can easily check that there are no possible. any other two-dimensional local algebra, three-dimensional local algebra is isomorphic to these two elements. Okay, if you have dimension 4, then there are 4 objects. If you have dimension 5, then there are 9 objects. If you have dimension 6, then there are 25 objects. These are already non-trivial results. This is not, you cannot modify them by hand. But this is the, sorry? I will come to this point, but up to now. So this is Arzhantsev. They refer to a paper by Superintendent Gorenstein. This is a contribution of the from Medical School. This is about commuting important matrices. But one can establish a judgments in some sense of the theory of commuting subalgebra and algebra of important matrices, about generated by important matrices, and such abstract local finite dimensional commutative association. And from the result of Superintendent Gorenstein's book, one can extract these results. And this is very nice number theoretical question. You have a sequence 1, 1, 2, 4, 9, 25. What will be the next term of this sequence?
36.
Infinity. So starting from dimension 7, you have infinitely many non-isomorphically local objects. So also it's a model.
What types?
So you can find one parameter family of non-isomorphic 7-dimensional local algebra. They write it in a different terms, but if you translate it to our language, it will be precisely.
And how many reducible components of this one dimension?
This is not studied as far as I know.
Or connected components, maybe.
Very natural question, and it seems to be people study, I don't know, modular spaces of curves and so on, but such a natural question, finite dimensional algebras. So, just one. We have finite fields. Everybody knows how finite fields look like. Simple finite groups, much more difficult, but nevertheless done. And next, extremely important algebraic object, finite dimensional commutative associative algebras. Okay, building blocks, local algebras. What about local objects? And even this classification was done independently by some Swiss mathematician, Mazdova, in the 60s. And there is nothing else in the literature, so only.
Didn't you parade?
This should be also connected with classification like Dobson issues on close, like in one lines.
Yes, some people connected it with functional Hilbert schemes on a finite plane and so on. So there are some. But say to describe some characteristics of this modular space, how many connected component or usable component dimension.
Dimension 7 is one dimension.
In dimension 7, this is one dimensional. This is no. This is because elliptic curve are parameterized by 1G invariance. This is maybe. But in general, I don't know. So
can you give a rough idea why elliptic curves give you different?
No, this is written in such paper and can be understood, but in some explanation. And also, if you want to study such algebra, there is a very useful object called Hilbert sum sequence. Maybe this is the first object you should consider when you think about local algebras. You have your algebra A. You have your maximal ideal. Then you may consider the square of this maximal ideal, and so on. But as this ideal is important, you will come to 0 at some point. So some, I don't know, S power of this ideal is 0. This is a sequence of subspaces. If you want to have number sequence, then it's very natural to consider numbers Ra, which are dimensions of highest power of my ideals minus the dimension of the next term. Okay, so the sequence divide all our local algebra in finitely many types. You can write down finitely many sequences of this form. Not any sequence can be realized in this way, but this is known from Macaulay time, which sequence can appear here. This is some 4 sequences and so on. And it's natural to classify local algebras of with a given dimension sequence of this form. For some sequences, there are finitely many isomorphic classes. For some, there are infinitely many classes. We try to study this with a paper by Konstantin Luminov, but this is also very difficult and non-trivial question. And one more very natural object related to local algebra is so-called socle. So, socle of A is the set of all elements in my A which annihilate the maximum A. This is a set subspace of all elements such that A multiplied by any element in my unique maximal ideal will be zero. Clearly, this last non-zero power of my maximal ideal, m power L minus 1, is contained in the socle. Because the next step you will obtain zero power. But it may be not the whole socle. Socle may be bigger. And very important definition for my talk is that the algebra A is Gorenstein if the dimension of the socle is 1. So Gorenstein means two things. Firstly, that socle coincide with this last non-zero power of my maximal ideal, and secondly, the dimension of this last non-zero power is 1. This is Gorenstein. Say this algebra is Gorenstein, because here socle is just the linear span of X squared.
But here, the definition of field A is local, right?
Yes, it is A local.
But this is also good for doing something.
Find the Gorenstein algebras of good dimension 0 are also for Venus algebras.
Okay, and in this case, this is not Gorenstein. Because here, socle will be the whole maximal ideal, which is the last zero power, but this is 2-dimensional. Okay, so there are two types of local algebras, Gorenstein and non-Gorenstein. And in this table with numbers, we can easily find which algebras are Gorenstein. Say among these 25 6-dimensional algebras, there are precisely 6 Gorenstein. So something like this. And if we have some geometric interpretation of our algebras, if we know that algebra is, if you know that algebras correspond to some group embeddings, then any property of this algebra should have some geometric meaning. Let me give this meaning in this concrete case. Proposition. A is Gorenstein if and only if the corresponding group embedding has a unique fixed point. This is obvious. It comes directly from a definition. Always there is a fixed point, but maybe there is a line or some separate fixed point. Gorenstein means that fixed point is unique for my additive action on the projective space.
Fixed points are just the projectivization of the socle.
Yes, yes, because the set of fixed points is the projectivization. Here there is nothing interesting. But I'm already almost out of time, but I would like to speak about another situation. I would like to say the following theorem. This is my section number 3. Can we apply this Arzhantsev approach not only to projective spaces, but to some other projective varieties. To take some projective variety, to associate some local algebra with some additional data, and in these terms, to classify all additive actions on such varieties. And, the idea was that this new projective variety should be not far from projective spaces. And which projective variety are not far from projective spaces. And different people may have different opinions, but let me say that these are projective hypersurfaces. So they are almost projective spaces. Maybe this is a stupid point of view. But nevertheless, we have additive actions on.
Also this theory view, yes?
This is a more or less direct consequence of Arzhantsev results. So there is no name difference. This is not maybe written explicitly in their paper. This is a direct consequence.
So x is dimensional minus 1, right?
Yes, so you have some hyper surface, and you want to consider additive action, effective action with an open orbit from such a hypersurface. And also, I will not know if that
doesn't necessarily extend to the actual.
Yes, this is the point. So this should extend. We call it induced action. I assume that this action comes from an action on ambient projective space.
But an action of GA n minus 1.
N minus 1. But this is a very nice question, but I should divide it into two steps. First step, is this action extend to the ambient projective space? Not always, but quite often we can guarantee that it extends.
No, it does here.
So?
No, it does. So the question, so if the dimension is high enough, then the question is what the degree of one, right?
So, okay, I consider only the hypersurface case. Okay, in this case, I claim that say if x is projectively normal, what is called, then it automatically extends. And we have some conceptual idea how to describe all non-extendable action from extendable. So I claim that in almost all reasonable situations, the action extends to the ambient space P.
Actually, is it the same as O1? The class is fixed with the curve?
Something like this. Yes.
Because there's no extension of J by GM, right?
Right. So we have some linearization technique for line bundles, but we should guarantee that we have a complete linear system. This is not some subspace in your complete linear system. Okay, sorry, I will not discuss this. But if we can extend this action to the projective space, this will be an action of smaller group. And we want to extend it to an action of a bigger commutative group, which acts as an open orbit. And this is always possible by Arzhantsev. So this is always an extension of subgroup action of some additive action on Pn. So our hypersurface is a closure of some codimensional subgroup inside of my additive action.
Right. So you don't assume that hypersurface is smooth, right?
No, for smooth, this is almost trivial. Because for smooth, we may have additive action only in quadratic case. This is quite easy.
Because the group is quite good.
Right. But the main thing is non-smooth and generally non-normal. So what you get is order closures. So, and this will be in correspondence with the following data. So AU, where A is again local of dimension n plus 1, and U is again inside of my maximal ideal, and the same conditions. Dimension of U is n minus 1, so dimension of algebra minus 2, and again this U generates A. So this is just a particular case what I wrote about cyclic representations. But now you have some technique to construct all additive actions on hypersurfaces. You should take local algebra, you should take maximal ideal, you should take hyper plane in this maximal ideal, which generates a whole algebra. And these are precisely the data which are in one-to-one correspondence with additive action. Okay, what is known? Let us take the case when Q.
Does correspondence remember the degree of the surface?
About degree. So if you have such a nice correspondence, then there should be also some algebraic interpretation of the degree of this x. Yes, we have. So degree of x is such a maximal number that this power of my maximal ideal is not contained in U. I like it very much. Because your ideal is nilpotent. At some point, this is U. So starting from some powers, this is contained in U. So degree of my hypersurface is the last D, such that this power is not contained. Okay? Oh, sorry, I should finish. I will finish soon. So I think that X is a Qn minus 1, which is non-degenerate quadratic inside of N. So you take a sum of n plus 1 squares equals 0, and this smooth projective hypersurface is contained here. I claim that there is a additive on this hypersurface. You can construct it by hand. You just write some orthogonal matrices, find some commuters with important subgroups, and blah, blah, blah. Another way is to look at this quadrix as flag varieties. You may consider the orthogonal group and take the first maximal parabolic subgroup, and then your quadrix is a flag variety with respect to this orthogonal group.
No, degenerate means smooth.
Degenerate means that this is smooth, that the number of squares is dimension plus 1. And here, for this homogeneous space, you may apply the Bjorn order. You know that if you take unipotent radical of your parabolic subgroup and take inverse opposite unipotent radicals, then this is commuted. And we know from Bjorn's theory that such a unipotent radical of a Bjorn subgroup acts with the open orbit, big Schubert cell on your flag variety. So you have additive. But non-trivial statement here is that such an action is unique. Additive action is unique. This is the theorem of my former PhD student, Elena Sharlyko, and it was proved exactly by this Hasuchinkin method. Elena proved that there is only one algebra and one hyperplane inside of the maximal ideal, which correspond to the additive action on the non-degenerate quadrix. If you consider degenerate quadrix, if this is a sum of squares, the number of squares is less than n plus 1, then you have many additive actions. Sometimes infinitely many, sometimes infinitely many, but definitely not one. Okay? So the very last point which we want to say, this is our theorem, but I should finish now, is the following. And now let us generalize it to higher degrees. Let us consider not only quadrants, but hypersurfaces of any degree. Then we say that such a hypersurface is non-degenerate if, in some sense, as the homogeneous polynomial which defines this hypersurface depends on all variables, So we cannot make a linear change such that this equation will not depend on some variables. If we can do such a linear change, if this hypersurface is degenerate, it just means that we have a projective cone over some hypersurface in projective space of smaller dimension. But we assume that all variables are essential. Okay, and we prove that additive actions on such non-degenerate hypersurface correspond to Gorenstein local algebras. And here that U, this local algebra A, which is Gorenstein, is are constants plus maximal ideal, but it looks like the following: this hyperplane is this maximal ideal, and the total, which is the last power, last non-zero power of the maximal ideals. So, sorry, I don't have time to write it down, but our theorem is that we can generalize Sharlyko's result to non-degenerate hypersurfaces of any degree. If your hypersurface is non-degenerate and if it admits additive action, then this action is unique. And we are almost sure that this is even only if case. All degenerate hypersurfaces have at least two different additive actions, but we cannot prove it up here. And I was very glad that such a natural condition that the hypersurface is not degenerate is equivalent to such a beautiful condition on the algebra that the algebra is constant. Say, maybe just one example. let me take P5. P5. And I have some hypersurface Q of degree Q. I claim that there are the following possibilities for the degree when we have a hypersurface with an additive action. D is 2, 3, 4, and 5. We can prove in general that the maximum possible degree of a hypersurface which needs an additive action is the dimension of the projective, not high. And as I told you, there are 6 Gorenstein algebras of dimension 6, which correspond to P5. And they are distributed among this degree in the following way. Here you have only one hypersurface of degree 2, this non-degenerate quadrants. Here you have 3 hypersurfaces. So there are 3 different cubic non-degenerate hypersurfaces which admit additive action in P5. And here again, 1 and 1. They are not smooth because I can prove that smooth we can have only in degree 2. But there are some interesting compactification, equivalent compactification of a fine 5 space, which are hypersurfaces in projective 5 space. Okay, so I finished. Any questions?
So in terms of this classification, can you see where you have only 5 equivalent orbits?
Yes, we can. This is quite easy question because there is only one local algebra which corresponds to actions with finitely many orbits. Because in this Cartesian correspondence between local algebras and additive actions, orbits correspond to principal ideal in the local algebra. So the question is, in which local algebra you have finitely many principal orbits? And this is the case only for this algebra. Only for one dimension, one generated local algebra.
So this is like projective space.
All local algebra correspond to projective spaces. But this is the only action of commutative unipotent group with the open orbit and with finitely many orbits.
Yes, what I mean is the orbit decomposition
Precisely. Affine space, smaller affine space, smaller affine space, and so on. And if you take another extreme, if you take the local algebra generated by n variables such that any squares, any products are 0, then you will have again additive action with an open orbit, but here you will have maximum possible number of orbits. Namely, you have an open orbit, complement is a hyperplane, and this hyperplane consists of fixed points. Okay, but there are many intermediate cases when we have more funny orbit structure, but in all intermediate cases, the number of orbits is different.
So does it follow? So suppose we have this compactification of the unipotent group. Does it follow that the element variety has a self-decomposition, which may not necessarily be?
Which variety?
Well, you have this compactification of your group with the extended action. So that this line of this compactification has a self-decomposition.
This is not true, because you should have it when you have finitely many orbits. But when you have subvarieties of orbits of the fixed dimension, we expect this and we try to produce some self-decomposition from this, but not now.
Yes, a question, please. Do you listen to me?
Yes.
Okay. What is a non-degenerate hypersurface? I didn't understand, sorry.
What is?
A non-degenerate hypersurface.
By definition.
By definition, once more. So how to get extra time for your talk? Not to answer some reasonable question during the talk, and then you will obtain this as a question. So no problem. Problems. I have a hypersurface S inside of my projective space, and this is given by some homogeneous polynomial in homogeneous coordinates, right? Any hypersurface is given by one homogeneous polynomial. And the condition to be non-degenerate means that it does not depend on all variables. It depends on a smaller number.
Okay.
But this may be not visible in this coordinate system. Maybe you should change the coordinate system such that one variable will be true. Okay. But if you like formally it's the following answer. You take the partial derivatives of your equation. And they should be linearly dependent. If they are linearly dependent, this is degenerate. If not linearly independent, then this is non-degenerate. Okay. Okay.
Yes. Another question, please, if it's possible. You said that A is Gorenstein if and only if there's a unique fixed point, and it's written on the blackboard. But in general, perhaps you said it, is there always a fixed point? You said there's a unique, the point is unicity, existence, or both in your proposition?
You take additive action corresponding to a given local algebra. If you have an additive, if you have an action of a unipotent group on a complete variety, even of a solvable group of a complete variety, you always have a fixed point.
Yes, because it's affine the orbits. Okay, okay, okay.
But this point may be unique or maybe not unique.
Okay,
so
okay, clear.
You can only use the algebra A is Gorenstein.
Thanks a lot.
Yes, thank you for the beautiful talk. So it's been a long time, but I remember we were looking at the following varieties and we couldn't resolve the following questions. So if you look at threefolds, let's say equivariant compactifications of GA cubed that have a fibration structure, for example, over P2 or over P1. And then, of course, examples of such compactifications would be like a projectivization of a sum of two, let's say, two line bundles on P2 or something like this. Now, are there any other models like this? So it's kind of weird. If your fiber over P1, for example, let's even assume that the generic fiber is P2. So you have like one singularity, like one degenerate fiber potentially. So what kind of threefolds can you obtain? That fiber over P1 is one bad fiber, generic fiber P2, and are equivariant for the GA cube action. So we found these kind of questions very kind of interesting, and of course your result about hypersurface is wonderful. So so maybe there's been progress since. It just said.
Unfortunately, I don't know about general threefolds because certainly it's interesting to classify all completions of a finite space. If you take just arbitrary completions, then maybe there are too many. If you have equivariant completions, this is some restriction of this class, and maybe this is possible to put some restrictions on fibers and so on to get. But why don't I study positive characteristic? Because I am not well educated for positive characteristic.
Oh, no.
Threefolds. Because I am not well educated in algebraic geometry.
Yes, of course, as rank Picard is one of the completions. There are papers that are doing this, but as soon as you allow just a little bit more flexibility, in these cases, when you have a vibration structure, then already things become very, very interesting. Anyway, so I thought maybe. Thank you.
Other question? Yeah, I wanted to ask a stupid question inspired by both posts. This one is the previous one for lunch. So these Kubikov-Khovansky rings are Gorenstein algebras in your sense.
Are they finite dimensional? Yes.
Yes. Can these two these two business.
So these two objects are separated only by lunch, and we should overcome this difficulty and to make some connection. Okay, thank you for your position.
Any other questions or suggestions?